Hi, and welcome to the third and possibly last video in our series about GaugeR&R. The last video ended with showing you a slide of a practice problem that you're going to complete and bring to class. This one we're going to talk about another concept of accuracy and precision, like you see across the top here. And you see 4 different graphs here. So we have a lot of accuracy, very high accuracy, but low precision because it's not on the target. Here we have high accuracy and precision because it's around the target and all the measurements are pretty close together. And then out here, low accuracy because it's not averaging around the target, and low precision because they're spread out. Here, high accuracy still, because when we take the average, we're still going to get at the target here, for example, center. But it is low precision because they're all over the place. So we want to be sure that we have a gauge that is accurate and precise. However, our GaugeR&R analysis will tell us about precision, how little or big our variability is, but it won't tell us about accuracy. It won't tell us if this measurement of 20 ounces is the actual, and may be very precise, but maybe the real weight is 22 ounces because the gauge hasn't been calibrated, or we don't have a golden unit to measure it against. So we need to be sure that we do that as well with our gauge system, that we have both one that is calibrated so that we know it is measuring accurately, measuring 20 ounces if it really is 20 ounces, and is precise as well. So our GaugeR&R studies really focus mostly on the precision, not on the accuracy of it. Another example we're going to do, so far the examples we went through were one operator only, and therefore we were able to isolate the variability in total between the variability of the part and the variability of the tool. Now we have a 2-factor experiment where we have multiple operators. In this example we have 1 operator, 2 operators, 3 operators, and to analyze the gauge system, we have each operator, which now we have multiple operators, so there might be some variability associated with the operator as well, measure each part 3 times. So operator number 1 measures part number 1 3 times. Operator 2 measures part number 1 3 times. Operator 3 measures part number 1 3 times. We're going to do an experiment similar, not exactly, but similar to this in class when we do our lab in class about GaugeR&R. So what we do though is we take this data, and this is the same example that Liz talked about in her video too, but I'm just going to add a few additional factors that, to what she talked about. We take this data, we run it through Minitab, and this table, as noted, there was also discussed in Liz's video. And if we run a GaugeR&R analysis using ANOVA, the ANOVA version of a GaugeR&R analysis, this is the table that comes out, as well as this is a table from the prior page, as well as this information comes out as well. So it tells you the variance component, how much, what the total variance is, what the variance due to the part is, what the variance due to the total gauge is. And so the variance due to the total gauge is the variance due to the tool itself, which is the repeatability, plus the variance due to the operator reproducibility. So we have the variance due to the operator of 1.3, I'm rounding, plus the variance due to the tool of 1.5 gives us the variance of the gauge of 1.8. And then this is percent. So the total variation is 100% obviously. In this case, 96% of the variation comes from the part itself, 3.6% from the measurement system, and of that 1% is from the tool, and 2.5% is related to the operator. We also have a further breakdown for the operator, is the operator specifically, and then the interaction of the operator and the part itself. Okay, so the questions we want to answer is we want to find the variability of the measurement tool, the operator, the part, and in total. And again, you know, we're going to be able to do that easily because it's listed there for you. And you can see here, this is the Minitab, way to run it in Minitab is statistics, quality tools, gauge study, GaugeR&R crossed. The reason that it's crossed is because we have multiple operators. When we have just a single operator, this would be nested. But here we have 3 operators, if you remember from the prior slide, right? 3 inspectors, 3 operators, and so this will be across GaugeR&R. So what are our conclusions about the measurement system once this ANOVA has been run? Is it good or not, and why? We would also want to focus on what area would we work to improve and how would we improve that area. Running the numbers is one thing. Knowing what to do with those numbers is why companies have engineers, okay? What is the precision tolerance ratio given the user specifications? And how would you describe the precision and the accuracy of this measurement system? And we just introduced precision and accuracy concepts in an earlier slide. So let's go over and answer those questions. So find the variability of the measurement tool. So we just said here, repeatability is the variance due to the tool itself, and that variance component is 0.5111. So the ANOVA gives you the answers to it. The GaugeR&R, the mini-tab output, gives you the answers to it. So the repeatability is the variance due to the tool itself. The variability due to the operator, it's this grand total of 1.29, and we have what's due to the operator from the operator themselves, plus the part operator interaction. So those two added together, remember we can add variances, we cannot add standard deviation. The sum of those two variances is 1.3, I'm rounding. And then the variance of the part is listed here. You know, I've noticed I've got it color coordinated to hopefully make it easier to point out too. So the variance of the part is 48.29, so that's the answer there, and then the total variance is 50.96. Okay, so what are our conclusions about this measurement system? Is it good or not? Why? So if I look at total variability of the gauge, total variability is 3.6, is 100%, 50. Variability due to the gauge, the measurement system itself, both the tool and the operator, is 3.6 of the total. So probably that seems pretty good. In the examples we've done, that's the lowest percent of total variance attributed to the gauge system of any of the examples that we did. So that's probably pretty good with that. Okay, so looking at it in that context, I would say that's good. What area would you work on to improve, and how would you improve that area? So if I'm going to work to reduce the variance within the part, is really if I want to reduce the variability, that's where I would start, because 96% of the variance is due to the part, right? So I would do some design of experiments. Remember, we talked about that earlier in the quarter. Maybe the use of materials, the process and how we run and produce the part, the equipment itself. Maybe some of those are introducing some variability into the part, and so is there a way that we could remove that? Secondly, I would work with the operator, because that's the second highest component, right? 2.6% versus 1% for the tool itself. So 2.6% is due to the operator part interaction. So maybe there's some training for the operator, maybe the environment is distracting or impacts their ability to remove or reduce variability. So I'd look at that. All right. Question number 4, what is the precision tolerance ratio given a user specification limit of 58 and 18? Upper of 58, lower of 18. Remember, the precision tolerance ratio is 6 times the square root of the variance due to the tool, which is 0.51, divided by the user specification limit, so that's 20%. So due to the tool itself is 20%, and if we remember our table, that is in the middle section, so that may or may not be acceptable depending on the application. And you might want to think about it to address it more specifically. Think of the application for your term project, or pick some product from a company that you've worked at or would like to work at and discuss it in terms of that, if 20% would be adequate or not. Number 5, how would you describe the precision and accuracy of the measurement system? So accuracy, remember, is that we know that the measurement system is measuring the right number is not the way I want to say it, but if the yogurt weighs 20 ounces, the scale is going to show it weighs 20 ounces instead of shows that it weighs 22 ounces. And so really, this study doesn't help us with accuracy. We would need to have make sure that our system is calibrated, need to make sure that we have a golden unit maybe to compare against to see that it is giving us what the actual weight, for example, in that. If we have very tight tolerances, then I would say we need to have a very accurate scale, right? Precision is low variability due to the gauge being precise. Remember back to our slides that we had before. So maybe the variability is low here due to the whole system, right, is only 3.6. Due to the tool itself is only 1. So that's probably pretty good. But if I have really tight tolerances, and maybe 40 is not really tight, but then 20%, maybe that is too high. So I have to look at it in the context of both variability due to the tool in total and also variability due to the user specifications with that, okay? So in this case, I would say it's a toss-up because I have a low variability component, variance as a result of the tool in relation to the total is very small, but yet given the specification limits, I'm in that kind of no man's land where it depends on the product and the application of what's happening. Okay, so it's a little difficult to answer those questions. And so these are the kind of questions that you'll have on data that you collect in class during our lab activity on GaugeR&R, where you'll run this kind of analysis on data that you actually collect. So to wrap it all up for GaugeR&R, we ended up only having 3 videos instead of 4. And we explained the basic concept of gauge capability. So we're trying to understand the variability of the measurement system versus the variability of the part, and to see if we need to do something about that. And we also talked about accuracy versus precision. Accuracy is we just need to be sure that we have a calibrated system, and precision that we have low variability within the measurement system. Then calculate and explain the components of variability in the measurement system. So repeatability, which is the variability due to the gauge, and reproducibility, which the gauge or the tool. Reproducibility is the variable due to the operator. Remember, reproduce, OOO, operator, OOO is how I remember that. We also talked about the precision tolerance ratio, so gauge variability relative to specification limits, and we talked about how to discuss the assessment, the analysis of the variability due to the measurement system in total, as well as variability of the measurement system in relation to the user specifications, the precision tolerance ratio, with some example problems. Conduct and analyze a measurement system's capability experiment. So we did it with the control charts based on the first 2 example problems where we had just 1 operator, and we used the ANOVA analysis out of Minitab for when we have multiple operators. And then we're going to do a lab activity in class where you're going to collect data and conduct the measurement systems analysis. Okay, so you should be ready to roll. We'll see you in class, and we'll have fun with the lab. Thank you.